I like signals. Block signals, clock signals, train signals, chain signals. Really hard to claim signals. Signals that are facing every which way, that will misdirect and confuse you and lead you astray. I like signals. I like signals, so I've made a video all about how I implemented them in my game. First, I talk about how the signals split the track into different sections and blocks. I then talk about the different types of signals that are supported in the game. These can be block signals, chain signals, free signals, terminal signals, and unidirectional or bidirectional signals. I then give an overview of how the train simulation works and how the signals and planes of signals work in the simulation. And finally, I give some idea of the type of things that you can build using the signals. If you're new to the channel, I've been making a train game called Steam Revolution. The idea of the game is that you connect rail lines across a map of Europe. You can only connect towns and industries that are within sections that you've unlocked. You unlock those sections by completing maps of the individual regions. These are smaller and easier to complete. The goal of the game is to be easy to complete and to have no resource constraints if you just want to have fun and complete levels. However, if you're the type of person who likes optimizing things and getting the best possible solution, then there's something for you as well. Every level is scored by the infrastructure cost and the cost of trains, and additionally, the time to complete the level is added. So your goal is to create a solution that is as efficient as possible, that is both fast to complete the level and doesn't use too many resources. You can then compare your results versus other people's in an online leaderboard. If this sounds interesting to you and you'd like to see how the development of the game continues, then subscribe to the channel and ring the bell button. A level is composed of multiple tracks. Those tracks are placed such that they alternate between curved and straight tracks. Each track can then have any number of signals placed on it. The signals divide the track into what I call segments of the track. Thus, there can be one or more segments in a track, and segments are not able to span between multiple tracks. A block is then the set of segments that are not separated by any signal. The main idea behind this is to handle junctions that are where multiple tracks meet. The junction will be enclosed by a block. If you can then limit a single train to be able to enter that block at a given time, then there can't be a collision between trains at the junction. Calculating how a track is split into sections and then those are combined into blocks is done during the simulation initialization. This is similar to the idea of compiling code before running it. The main point of this initialization is to convert the representation of the tracks from something that's easy to edit into something that is static and fast to simulate on. During initialization, I can detect various different errors that are going to be determined statically just from the layout of the tracks. For example, if a track goes through a building, or if a track goes underwater, or even some problems with signals, such as if a block is in a loop and connects to itself. If any errors are detected during this initialization phase, they'll be shown with a dialog box that points to where they are on the map. Besides splitting up tracks and preventing trains from colliding, signals serve another role. Whenever a train passes a signal, it detects if there is a train station next to that signal, and if it can do any loading or unloading of cargo. Thus, building a train station is really easy. You just place a signal, and you place some platforms such that there's a path from the train to the industry, and then loading and unloading will automatically happen. Because the structure of a train station is inferred from the relative position of building blocks, you can build complex and interesting train stations that fit the layout of the space you have available. I have a few different signals, the type of which is indicated by its color. The simplest signal is the block signal, which is colored blue. When a train reaches a block signal, it can only proceed if there's no other train in the following block, or that block hasn't been claimed by another train. Chain signals are indicated by the color yellow. Chain signals are kind of like block signals, except the train can claim multiple blocks. Specifically, a train can proceed past a chain signal if any of the exits from the block is open. It's called a chain signal because chain signals can be chained together. If a chain signal is at one of those exits of a block, then it will in turn look at its exits. And if those exits in the subsequent block contain a chain signal, then that block will then look at its exits. And this can happen recursively for as many chain signals as you have. Chain signals are useful for coordinating more complex behaviors. For example, if you have one terminal station and multiple trains that want to enter it, then it will coordinate between those trains. Alternatively, if you have a train station with multiple different platforms, then trains can be directed to whichever platform is free. I've designed my chain signals to prioritize the shortest next path segment. Because you have freedom in placing where the next signal is, this allows you to prioritize some directions over others. For example, although it's not the shortest overall path, you may want to choose a path that gets your train to the platform that's closest to an industry so that it loads and unloads faster. Free signals are indicated by the color orange. These are sort of the opposite of a block signal in that they won't block a train from proceeding. However, trains will still stop at them to load and unload cargo. The idea behind free signals is to avoid a problem that exists in a lot of different train games. For example, in OpenTTD, you need to place tons of signals along straight sections of track to prevent trains from running into the back of other trains. This seems rather tedious and a bit silly. It also makes editing a track a real pain. If you want to modify how the track is, it requires resetting a bunch of signals when you wouldn't really need a signal at all. Or at least you don't need a signal so long as trains are able to look ahead, detect that there's a train in front of them, and to slow down if there is. This requires a bit more logic in the train during the simulation, but is totally worth it from an editing standpoint. This collision avoidance only looks on the track immediately in front of the train, and so it isn't able to handle junctions. For junctions, you still need to place other types of signals. Terminal signals aren't drawn on the map or directly placed by the player. Rather, they're something that the initialization algorithm will automatically place at the end of any track that doesn't connect to another track. Whenever a train hits one of these terminal signals, it turns around. After turning around, it basically acts like a free signal. If there's a platform that the train can load and unload from, then the train will do that, and otherwise the train will proceed. In terms of animation, I guess it can look a little silly for a train to just immediately turn around. However, this is what OpenTTD does, and I don't think that's all that objectionable really. And not being able to have a terminal station would be annoying, and the alternative of placing an engine on both ends of the train would take a lot of space and also look pretty silly because older steam trains didn't do that. At any signal location, it's also possible to specify any type of signal in either of the two directions. The most common option is probably not to specify a signal in one of the directions, and whenever a signal is not specified for a direction, that means that trains are not allowed to go that direction. This seems like a clean approach both visually and conceptually, and I like the way that it looks a lot better than, for example, how OpenTTD does it, where there's like a red line drawn on the back of a signal if a train is not allowed to go that direction. Before I go into details about how the simulation actually uses the signals, go ahead and hit the like button if you've liked this video. I'm going to explain how things work, assuming that the algorithm is single-threaded. If things are processed in parallel, then there are a bunch of complications and details and caveats that I would need to go into, and that's not really necessary for this overview video. If you're interested in those details, though, I do intend to make some videos about how I parallelize the simulation later. Regardless, the multi-threaded and the single-threaded algorithms need to generate identical results, and the simulation is completely deterministic. At least I hope it is. In terms of simulating train movement, there are 5 basic steps. First, trains update the segment and block occupancy of tracks. Next, trains propose where they would like to move to. If trains reach signals, then they'll be placed into a waiting queue. Next, all of the waiting trains need to have their waiting status resolved. Based on that, then trains will then commit their movement. And finally, I detect intertrain collisions. Let's go into a bit more detail about all of these steps. The first step is to determine the track occupancy. Conceptually, the easiest way to think about this is that each segment and each block has a list of train IDs that are in that segment or block. You can then find the occupancy by first clearing all of those lists and then going over all trains, then all cars of those trains, and add the train ID to the segment and block. You also will need to add any of the chained claimed blocks that the train has. If you saw my previous devlog about how I optimized the simulation, you'll note that I initially implemented it this way, but then I changed the implementation to be more efficient. Now I do something that has the same effect, but I update the occupancy iteratively when trains move into or out of blocks. Next, I need to propose a new location for each of the trains. First, there's the physics part of the update. Here, based on the power of the engine, the weight of the train, and the slope of the hill, the acceleration is determined, and the speed is updated. This is also where the max speed of the train is capped based on the curvature of the track. Next, trains need to search in front of them to find if there are any trains in front that they need to avoid colliding with. This search and collision avoidance is what allows free signals to work. The segment occupancy update needed to run before this so that trains are able to find what other trains exist on the track. If a train is found that has gotten too close, then the following train will try to match speed and maintain a minimum follow distance. Also, whenever a train gets to the end of a segment, then it needs to switch to a new segment. In general, a train will have a path that's following, which is encoded as a list of segment IDs. So whenever a train gets to the end of a segment, then it will pull out the next ID from that list. Sometimes the list will end at a signal, in which case the train needs to be placed into a waiting queue, and the list will be updated at a later time. The next phase is to resolve the queue of waiting trains. Trains are processed in the order that they arrive at signals, and tie breaks will be based on the train ID. And the train ID is based on the order in which the trains are created. When a train is processed in a waiting queue, first it will turn around if it's at a terminal signal. Then it will load and unload cargo if that's an option. Then it will try to reserve the next block to move into. If the train doesn't already have a path, it will try to generate a path of segments at this time. Additionally, the path that it reserves may cross multiple blocks if it's waiting at a chain signal, and this is calculated recursively. If a train, for whatever reason, for example, if it's loading and unloading, or if it's blocked at a signal, will have an invalid next location set. Next, we need to commit the movement of the trains. If the train has no valid path, then the speed is simply set to 0. Otherwise, the proposed location is copied into the actual location of the train. All of the cars following the engine are then updated to move the same distance that the engine moved. The final phase, in terms of train movement, is to do collision detection. If trains get too close together, then they crash, and hopefully this doesn't happen very often. The details of how this is implemented isn't actually very important. The main thing is to know that this is the justification for why we have signals in the first place. Without the ability for trains to crash, there's no real reason to protect junctions against trains crashing. And with that, we're done. Once we have the basic building blocks of tracks and signals, it's possible to combine those into more complicated structures. The possibilities are endless, but some examples of those structures are splitting junctions, merging junctions, level crossings, bidirectional passing locations, roll-on, roll-off stations, terminal stations, overpasses, and many more things. I'd love to hear what you have to think about this. Was everything explained clearly? Do you have any questions? Go ahead and leave a comment down below, and I'll probably respond to you. I also have some other videos that you may be interested to check out.